Okay, morning everybody. Let's get started. Any questions about the interim videos, user testing? We're all good? Okay, so let's switch over now and talk about looking inward. We've spent a fair bit of time over the past few weeks talking about technologies that are being designed to interact more and more directly with the physical environment. Now we are going to come back to the human user and the human observer, who pushes against the world and expects certain ways for the world to push back. And we're going to think about that particular feedback loop very carefully. So recall our discussions about mental models and expectations. How do we go about building virtual environments in which when we push against the virtual environment provides a sensory repercussion that we expect. So we'll start today with virtual reality. We'll probably finish that today and then move on to augmented reality, where we're layering aspects of a virtual world on top of the physical world. In augmented reality, we're getting reactions from the physical and the environment and the virtual environment simultaneously. Not an easy thing to do to make sure that both of those streams of repercussion match up and are what we expect. All of those technologies so far are goggles over the skin. We're going to then switch and have a three-part lecture on Cyborg Technology, where we're going to look at interactive devices that are partly or completely under the skin. How do you think about cybernetic technology that is augmenting or replacing parts of the physical body? But again, the brain is sending signals to those devices and expecting certain signals coming back from those devices. A very intimate form of HCI, and we'll finish the course with that. Obviously, we've got lectures next week. The following week is Thanksgiving break. Next week, I will talk more about the user testing that you will be doing with friends and family over the Thanksgiving break. We'll talk about that then. All good? Okay, so virtual reality, always a lot of fun. Not just fun, but becoming increasingly lucrative. I just pulled this off the web yesterday. It's an expectation that over 152 billion US dollars will be made on video games in this year alone. Even more surprising is looking at the rate of growth, 10% per year. It goes back quite a few years. A 10% growth rate is pretty shocking. You can see the breakdown here in terms of console games and mobile gaming. Hold on to this figure of 152 billion for this year. Let's look at the domestic box office, so US dollars earned for top grossing movies over the same year. The most popular movie this year made less than $1 billion, 0.8. Second most popular made 0.5. The two most popular movies together grossed 1.3 billion. You can keep summing that number as you move down the list here. I think it was 2 years ago the gaming market grew larger than the box office and continues to do so at an incredible rate. Okay, so huge market. Computer games have been around for quite a while. We're now moving into the world of virtual reality, where we are trying to place the human observer inside the computer game or the virtual environment. We're going to watch a video in a moment which is basically a promotional video for 5 different virtual reality systems. I think this video is a year or two old, so already some of the systems in here are a little bit outdated. You'll notice from some of the names that we are going to look at systems that are not just goggles, but provide the affordance or the ability of the human participant to move in the physical world and also move inside the virtual world. So when you watch these 5 videos, get out some pen and paper, and I want you to note down for these 5 different systems, what are the particular sensor motor feedback loops that are occurring? And is the system supporting what is expected of that feedback loop or frustrating that feedback loop? So if, for example, the human user is wearing virtual reality goggles and they move their head to the left, what is the sensory repercussion expectation that they have? You're wearing goggles and you move your head to the left. What do you expect to see in the screen inside the goggles?
Camera's right.
Camera right? So your visual field should move to the right and vice versa if you move your head to the right. It's taken a long time to get that right. Most of that is sort of engineering improvements. That's pretty good now in most VR goggles, but it's not perfect. So there are going to be some subtle aspects when you watch this video of some of those features that frustrate expectation. So in all the goggles you're going to see in this video, when the user moves their head to the left, the visual field moves to the right. But if there is a small amount of lag, that frustrates our expectation. When I'm looking at the physical world and I move my head, I get an immediate visual repercussion, immediate visual feedback. If there's a small lag, aside from frustrating the user's expectation, what else can happen? Has anyone ever tried VR goggles with the lag?
Yeah,
you get nauseous, right? So there are actually physiological repercussions of frustrating the expectation of a mental model. Okay, so again, we're going to see not just goggles and head motion, we're going to see full body motion, arm movement, leg movement. Try and catch as many of these feedback loops as you can, and how well or how poorly are these various devices supporting or frustrating the expectations of those feedback loops. Speaking of rich virtual environments, it's taken me all semester, but I finally figured out the audio, so we got there. Better late than never.
Today we're checking out VR treadmills that are either currently on the market or under development. These devices add locomotion to the VR experience, designed to increase immersion. Let's check them out.
Catwalk is a new omnidirectional treadmill input device. The main problem Catwalk solves is to move within a small space in reality and achieve limitless and continuous movement in virtual reality. With its built-in and wearable sensors, you can literally walk, run, backwards, jump, crouch, and sit in the virtual world. Different games call for different movements. Catwalk allows you to switch actions anytime you want. You can even sit down to drive or fly when a game requires it. We started the project since 2013, and we have made quite a bit of prototypes. During developing and testing, we noticed that in many games, you want to perform different actions with your arms and legs. It was annoying and disappointing if these movements are constrained. And while in a virtual world, you can't see the real one if there are devices near your arms and legs, think or get hurt. The creative Catwalk independent support structure and open construction sets your arms and legs free. First, it is very easy to get in. Without a ring or column surrounding you, you can move freely without constraint or worry about hitting anything. You can swing your arms naturally or put your hands to rest down by your sides, getting closer to a natural walk posture. Catwalk has not just simply removed the column and the ring. Our unique design can limit the horizontal moving range and control the vertical movement function while walking and running. It can automatically provide 35 cm vertical moving range while jumping, crouching, and sitting. Meanwhile, it can help users move back to center to adjust the position offset while walking, which can increase the sense of balance and safety. When we walk in real life, friction is what propels us forward. Frictionless walking is awkward, like walking on ice, if you must pay attention to keep balance. Catwalk uses high friction material surface and uses a constant force of rolling friction to simulate real walking forces and human motion. This makes you feel like you are walking on real ground instead of sliding walk. With normal friction, it is easier to keep balance. Decrease the time it takes anyone to learn to use Catwalk. Catwalk uses a lower cambered base to transfer potential energy to kinetic energy and to reproduce the movement locus. All of this is to achieve a more of walking. You can use it to enjoy relaxing virtual reality games or applications in a comfortable way. Just sit back and relax. Our software can transfer body motion to keyboard or gamepad. This means all the games with keyboard or gamepad support will be playable. We are also developing our own SDK and demo to achieve analog movement and independent walking and looking direction. The prototype you see here is kind of big. This was made to prove our brand new solution. We already have all the plans to make it smaller and lighter.
everyone here, and thanks for coming to our office. It's a big week for us. This week we delivered the first.
It's kind of where games have always been trying to take you. They always talk about immersion and trying to actually put you in the game. Well, you can't just do that with only a console, a controller, and a TV. It is immersive, but you know you're still sitting on the couch. Hopping on something like the Omni, where it puts you in the game and it's like you're shooting that to get into the battle.
I have an extremely bad problem motivating myself to do exercise.
Yeah, I broke a sweat in like that short amount of time. Is it get the heat turned up in here? I don't know.
Getting to enjoy that physical interaction of running and moving and looking and not feel so detached from the world that you're playing in. It's night and day.
I have told people for years, if I could walk across Skyrim, I'd be more fit. And this is exactly that machine. I was like, oh my god, somebody actually made that thing.
I mean, I'm not much of a shooter. I just want to go explore a world, go running in, you know, a world full of dragons and magicians and whatever.
The biggest thing right off the bat is
So far, all of my experiences with seated VR, like I had motion sickness stuff, and I had none of that here.
What I loved about it is you're actually playing with people.
the last time when I tried was single player. You kind of walk through this corridor. This one was a little more wild because I had a partner there right next with me.
When the bad guys get close to you, you instinctively, like, you move your body away from them, you react. My head moved, and it moved, and my whole body went with it, and it was cool.
I could have this in my living room with my rock band equipment, and I think that's really exciting.
The virtualizer consists of three main parts. The base plate with a low friction surface, the pillars, and the ring construction. There are linear guides in the pillars that allow for smooth and quiet vertical movements. This is for crouching and jumping. And in addition to that, the ring construction allows the user to turn around and rotate 360 degrees. We felt that rotating inside of the second prototype was as we wanted it to be, so we decided to improve the mechanism of the ring construction. Furthermore, we also refined the sensor system that detects the rotation of the user. We've also changed the linear guide system inside the pillars, which is now smoother, more quiet, and more durable. On top of that, the new system is lighter than the previous one, so we have saved some weight. Another major improvement is the material that we use now on the base plate. For us, it is very important to have natural walking and running inside the device. So the friction coefficient is now on a level which is ideal for natural movements. When we started developing the virtualizer, we made some experiments with different shapes and also made a motion analysis in the laboratory. We also tested the different shapes in action. And we have realized that the flat base delivers the best immersion. Now, if you use a bowl shape, it will touch the slope of the bowl earlier than you would expect, creating a discrepancy between what you see and what you feel. This breaks immersion and pulls you back into the... Stability is very important for us, so we decided to use 3 pillars instead of 2 or just 1. The reason is that 3 pillars absorb the forces and the momentum caused by the user rather than 2 or just 1 pillar. And since we were able to sit down in the virtualizer, we had to make sure that the construction supports the user's weight.
Speaking of the sitting function, obviously you have to be fixated inside the ring to perform moves like jumping and crouching, and also of course to sit down. Does the user have to carry all the weight of the ring construction as well while he does so, or do you have a solution for that as well?
We have a special construction in the pillars, in the linear guides, which compensates the whole weight of the ring construction, so the user doesn't have to carry the weight and doesn't feel anything with the ring construction.
Okay, so one thing you notice about the new prototype is that you've constructed a black bar, which is hanging above your head now. Could you maybe explain the reason for it being there?
Yes, we call this platform VR, and it is constructed because of head-mounted displays and earphones which are wired.
Okay.
So you can guide the cables over your head, but don't get disturbed with the version though.
Okay.
And it is designed that way that you can still aim upwards without tossing against it.
I see. So it's all completely unrestricted.
Absolutely.
Okay, I see. Okay, look, I think that's enough for now. Thank you for taking the time off to show us the virtualizer.
You're welcome.
Okay, I'm just going to pause the video here, and let's talk about the first three we just saw. We'll watch the remaining two in a moment. Let's start with the first one, Catwalk. What were some of the design aspects there that helped to support the expectations of this feedback loop? There's no ring, right? So in the second and the third one, there's a ring. You can feel that obstruction. Yep. So there's a clear theme throughout all three of them, right? Is trying to clear the range of motion.
They had to design rollers for their shoes that mimic friction experience.
Exactly, right? So the high friction rollers on the shoes for the Catwalk for the first device to mimic walking. How so? So the third one that we just saw, they had low friction solution. Why high friction for Catwalk and low friction for the third?
For Catwalk, they wanted high friction to walking, and what they were saying was that if it was low friction, it would mimic ice or sliding on ice.
Exactly, right? So if you walk to campus this morning and you hit any ice, it's already uncomfortable. Imagine if you couldn't see your feet or you couldn't see the lower part of your vision. Extremely difficult. Yeah.
Well, because the high friction, they had to basically make it in a bowl.
So the first and the second one had this bowl. What was the idea behind the bowl? Why have a concave surface to walk in rather than the flat platform in the third device?
I guess it's can get you automatically to the home position.
Exactly, right? So obviously you need to keep the person in a particular location and keep them there without breaking the illusion that they're actually displacing or moving in the virtual environment. Tricky thing to do. So the bowl is a nice kind of low-tech solution where the center of mass is naturally going to slide back towards the home position, the vertical center. Yeah. What other aspects of these three supported or frustrated the expectations of the observer?
They all have a functionality of a seat, so you can sit on the virtual environment.
Exactly. Yep. So something to support sitting.
What I noticed with the bowl was that you had to actually teach the user how to walk again.
Exactly.
The steps are very constrained, so it's not a natural step, so they have to figure it out for a while before they can just jump in and use it.
Exactly, right? So there's some cost with this concavity solution where you have to train to walk in it. Why? If there's training involved, it means that there is some mismatch between the physical expectation and the virtual reality. What is it about the bowl what is specifically is frustrated in this feedback loop?
Your foot hits the bowl before you expect it to.
Exactly. Your foot hits the bowl before you expect it to. If you've ever stumbled on the stairs where you hit a stair earlier or later than you expect, it's a very frightening experience, right? There's definitely high expectations that your nervous system has, especially when it comes to walking. Yep.
I'm not quite sure if this is conveyed, but it seems like since it's a bowl, that you're always going to feel like you're stepping up an incline, and that's not always the case.
Exactly.
But then with the flat version, it's the reverse, where you don't have any opportunity for incline.
Exactly. That's it, right? So it would be hard in the virtual environment to have something other than a flat floor. Or is it? Imagine you wanted to deploy a game for one of these three systems where you had to climb stairs. Is there a minimal modification they could make to the hardware software setup to help cast the illusion that you're actually stepping?
I don't think it would be minimal.
Okay.
It seems like you could maybe try to have like a thing that pops up and then like goes down with like a certain amount of resistance when you step on it.
Absolutely. So we could roboticize the floor a little bit. Maybe we have some risers that are triggered by the game, which is a good idea. Lots of safety concerns there, right? Now you've got things that are moving under the user's feet that they cannot see, which is fine. But again, we've got this trust system, the support system, lots of interesting physical context within any one of these VR systems. Yep.
Not the exact same mimic stairs, but you can kind of make it like a treadmill with this anchor point that goes up or down.
Possibly, yeah. There's an idea. So we could do slopes, maybe. Yep.
We watched a video a while ago about like big sensors in there.
Yep.
Like,
That's right, exactly. The whole, if you remember the ultra haptic system, which sent out pressure waves into the air, which would simulate that you're in contact with an object. There are attempts underway to integrate ultra haptics with VR systems. Now, it probably wouldn't be for something you'd step on because obviously there's nothing there to actually take your weight. But if there are virtual objects in the environment that you're trying to grasp or manipulate or collect, that might be, the ultra haptics might be useful in that context. Yeah. Anything else you noticed? Someone mentioned the lag and feeling nauseous.
I remember reading an article quite a while ago about the reason why these aren't successful is because when people come home from work, it's a good novel idea to get on a treadmill for a little while.
Right.
But you don't want to go running around for an hour and a half in some combat zone after a long day. You just want to sit down and click it out.
Possibly, right? So
your physical fitness aspect as well.
So then there's the acceptance issues about VR, right? Some of these might be a lot of fun and they might be engaging. So they may fulfill that non-functional requirement. They cast a good illusion, but is it something that people actually want to be involved in for an extended period of time? Maybe yes, maybe no. Somebody mentioned that they did break a sweat. So that's another clue about a certain feedback loop that is being supported. Whatever it is actually taxing your cardiovascular system. Should we move on? Okay. Somebody mentioned a treadmill.
Welcome to Infinidec, a true omnidirectional treadmill. Infinidec uses motorized components and a simple belt connected to a sensor to track and respond to your movements in real time. Infinidec's belt has multiple bands that change direction, allowing you to go in any direction at your own, freeing you to explore your virtual reality environment naturally and safely. Infinidec revolutionizes virtual reality movement, giving you the ability to quickly change pace, stop and go, crouch and pivot, providing a truly immersive experience. With our technology, you can feel like part of your favorite game, or jog through exotic countryside while at the gym. Infinidec makes the future possible today. Imagine training simulations that prepare you for urban warfare, let you practice tactics on foreign terrain, or even walk beneath the stars of another world. Infinidec's omnidirectional treadmill technology makes it possible for you to be fully engaged in the VR world while keeping you safely in the center of the treadmill. There is no limit to it.
Okay, I think you get the idea. Is the Infinidec more realistic or less realistic than the concave depression surface, just in terms of walking? It's hard to say, obviously, unless you try it, but there are several hints in the video.
I think this one has a little lag.
It has a
little lag.
a little lag, right? So you'll notice that as the user starts walking, there's a bit of a lag until the treadmill detects it and starts moving.
I also find that, at least when I'm running on a treadmill, it's not the same as running on a surface because you're actually being propelled backwards, I guess, in a sense. It's kind of doing some of the work for you.
That's it. So you can think about these omnidirectional treadmills and you can build up an intuition for it if you've ever run on an actual treadmill at the gym. Like you're saying, it's not the same as running in real life. Why not? Let's talk about traditional treadmills first. What aspect of the experience of running or jogging is not supported by a stationary treadmill? Turning, okay. Or let's restrict our discussion to jogging in a straight line. That's also missing something. What is it missing?
The motion detector in our ears.
Okay, exactly, right? So the acceleration data that your inner ear provides, so obviously when you're running, you're accelerating forward in the direction that you're looking. And when you're on the treadmill, there's a little bit of that when you lurch forward, but then once you reach steady state and you're jogging on the treadmill, there is no non-zero acceleration in any one direction, right? You're more or less stationary. There's a bit of vertical acceleration and deceleration. So that feedback loop between movement and vestibular sense, your inner ear, which tells you information about acceleration and orientation of the head relative to gravity, that is not supported very well. But most of us can run pretty well on a treadmill. If you've ever stepped off a treadmill suddenly after running for a while, what happens? You feel like you're moving a million. So what happens at the moment you suddenly step off the treadmill? So some people feel like they're still moving or feel dizzy. What's happening? Why? It's not the same as lag. It's not the same as nausea induced by visual lag with goggles. It's
unnatural deceleration.
It's an unnatural deceleration. So running on a treadmill is unnatural to begin with. You're going from a natural back to a natural environment. What's happening?
Because running on the mill for a second, your device adjusts to the expectation.
Exactly.
So stop. It's still want to get some feedback.
So the brain is a prediction machine. It's making predictions about, as I'm running, what I'm going to feel in my inner ear, what I expect to see. And if that expectation is frustrated, and frustrated consistently, which it will be if you run on a treadmill for an extended period of time, the brain adapts and updates the predictions that it's making. So a bit of a metaphor again, if you have your KNN algorithm and halfway through a session with your KNN, you add some more training data to it, it adapts. It has more data and it will start to alter its predictions given the new data. So your brain starts to adapt and predict what's going on the treadmill, and if you suddenly step off, those new expectations are suddenly frustrated and you feel like you're moving or you feel dizzy and so on, right? So in an artificial system, like a normal treadmill or a VR system, we might frustrate the user's expectation, but if they use it for a consistent period of time, their brain will start to adapt and make new predictions, right? Something to keep in mind. Yep?
I have a new idea. If they make a fan on the machine, and,
Okay.
It can generate some wind.
Exactly. So your skin makes predictions as well when you're running naturally. Yeah, exactly. So we could add some additional technology to try and improve the illusion. How does the Omni treadmill work itself? Let's just talk about the treadmill for a moment.
How do the corners work?
How?
When you shift the treadmill around in different directions, how do you get corners?
Exactly. So let's talk about the treadmill itself. So a traditional treadmill at a gym, you usually have a forward and a backward roller, and they're rolling the mat. What's going on in the omnidirectional treadmill?
I would guess that it's only kept taut on the top, and it kind of sags beneath in sort of like a spherical-ish shape.
Okay.
Because, yeah, the corners, things like it's
Possibly.
Maybe like disjointed segments in both directions on ball bearings.
So if you go back and watch the video at your leisure, you'll see that there isn't one mat wrapped around the forward and back roller. There is a forward and back roller with a material wrapped around the forward and back roller, but that material is made up of separate smaller rollers that are rolling a thin band like a rubber band left and right, while that band is being moved forward and back by the larger system, which gets around the issue of corners, right? So again, by intelligently controlling the relative motion of the smaller rollers plus the larger roller, you can get the whole surface to move left and right and forward and back. But there's this lag, right? Little tricky. Yes?
There's also a part where you have this kind of running and you stop and move.
Exactly, right? So it takes a while for the system to detect that you're accelerating and for the rollers to accelerate in the opposite direction to keep you in the same place. But of course, once you stop running, it also takes the rollers a moment to react and slow down. How do the rollers know when the user is accelerating or decelerating and in what direction?
I mean, to me, it kind of looked like with less friction when you get on a treadmill that isn't on, and like it didn't recognize it a couple times when he was moving, so you have to like physically start to like move the treadmill, which is an issue in itself. Like it's not really sees it.
Yeah, possibly.
Yeah, it looks like with less friction, but it is kind of like not noticing all and not stopping.
Exactly. Yeah, so there's someone was on there with socks, I think, right? So there's some low friction. So is it friction that the treadmill is responding to?
Kind of like direct pull.
Exactly. So if you have high friction, then it can feel maybe the pull on the rubber mats themselves, possibly. That might be part of it. It's hard to tell from the video. What else?
It kind of looks like the whole setup
Yep.
kind of behind them was, because that's like at their center of gravity, it looked like maybe that was indicating their direction of acceleration.
You mean an external camera?
No, because they were sort of held in a belt.
They're held in a belt. So put yourself in the shoes of the device itself, right? You have to send commands to the rollers to move in the opposite direction of the human. How do you detect the direction that the human is moving in?
I'd say it's the pressure based on where the foot is at the time. So if you see when the guy was on his knee at first and they tried standing back up, because he was standing up with his toe, it went back on him and he had to catch himself.
That's it.
So I would say the bar behind was just telling the machine where the front and the back of the foot would be.
Exactly. So it has to do with the foot itself. You'll notice when the guy's kneeling, and he stands back up, he's on his toe. So there's the local pressure of the foot is suddenly asymmetric. There's much more pressure on the balls of the feet, and the heel has actually come off the ground. And at that moment in the video, you see the treadmill start to respond. So that's a pretty strong hint. So it's using the relative mass distribution in the footprint of the user. Why and how? What is it? How does that tell you something about the motion of the user?
If you're stepping forward, your heel comes out. I guess if you're running forward, most people their heel comes up first, and so if it's a smaller footprint and it's shifting, I guess you'd want to shift it in the same relative speed that I guess it's moving forward.
Correct. So imagine that the user's foot is flat on the treadmill, completely flat. Now they've either been lucky and landed completely flat-footed as they're moving, but of course this is something that's going to integrate over time. If we take the flat foot and detect that there is increasing pressure or weight on the balls of the feet, not just is the mass distribution now on the foot, which means the user is starting to shift their center of mass forward, but if you can detect the change in distribution of pressure in the footprint, you can get acceleration. Are they walking or are they getting ready to move quickly? In the video, they also take a few back pedals, which you can also get by detecting increasing weight on the heel of the foot. if I'm going to pivot and start to turn to my left, walk to my left, or run to my left, what information is needed to detect that particular action and respond appropriately? One's a little trickier.
Maybe a shift to, if you're standing upright, you shift to one, the leg you're going to be pivoting towards.
Possibly. So I can shift from my weight from one foot to the other, which isn't enough to tell the system about whether I'm turning to my left. We're really digging down into the details now of the biomechanics of human walking, which is the physical context that's relevant for this system. What information tells the device that the user is starting to turn to their left?
If you were turning to your right, it'd be like the big toe side of your left foot, be like a certain side of the balls of your feet.
Exactly. So you need now pressure information about the left and the right side of an individual footprint. You also need torsion, which is the amount of force that I'm twisting about my long axis, which you can also get from pressure information from the feet, but it's a much more complex signal. It's an incredibly difficult thing to do just through human intuition. So you can imagine the designers in this case fell back on. So rather than trying to figure this all out by hand, if you want to try and figure out how the treadmill should respond accordingly to complex movements like walk forward, walk back, run forward, walk back, twist left, twist right, go down on one knee, back pedal, how would we figure all this out?
There's a device on the player's waist.
Okay.
Yeah, so indicating that you are turning around or up and down.
Okay. So we could decide to use information maybe in the bar around the waist. Use a machine learning algorithm, right? All of the above. Collect pressure information from the feet through the treadmill. If there, whatever information is in the bar, perhaps an external camera. Put someone in the device and start collecting training data. And you can imagine you're going to need a lot of training data for this problem. And off we go. What could possibly go wrong? So we're going to train a machine learning algorithm to properly move the treadmill in response to the human movement, but we're not there yet. We haven't trained it yet. So what's going to happen to our human trainer that's in the harness?
It might fling them out of the harness.
It might fling them out of the harness. I try and accelerate forward, and the treadmill helps me with that. Luckily, I'm wearing this harness, so I'm not going to get flung out of the actual device. Let's assume that actually happens. So the treadmill moves in the wrong way. Is that usable training data for the machine learning algorithm?
If the person in the machine is able to somehow score how much their mental model is matched or broken.
Possibly. Maybe we give them a console and they just click yes or no. Did that feel familiar or unfamiliar? We could ask them explicitly to do that while they're being thrown around by this randomly moving treadmill. Remember, human testing is very, very important in HCI. How would we go about doing user testing well in this system? First of all, to make sure that the human trainer is safe. And second, to make sure that we can collect enough clean data to train the treadmill to move properly. Not an easy thing to do. Yep.
Could you tell it in advance what it was going to be seeing?
Possibly.
Leave it in neutral, basically, like that's a big block on it, and have it know that that is what it needs to do.
So we could try and set up a steady state system where the treadmill moves like a familiar treadmill, or we set it to move at 45 degrees and ask someone to move in the opposite direction. Yep, we could try and do that. That would be one way to approach this. Possibly, so maybe we do some simulation before trying to do some physical testing. Probably a good idea if we're going to be involving human subjects. So if I'm the human trainer and I'm in harness and I am trying to walk in different directions and observe how the treadmill moves, and the treadmill moves in a way that I wasn't expecting and I stumble, do we have to throw away that piece of training data, or can we use it in some way? We probably don't want to use the last few seconds of that interaction because I'm causing the problem now. I'm stumbling, which is generating non-standard pressure distributions on the soles of my feet, which is not something that should be supported by the device. So maybe we have to think very carefully about what time slice we take out of that interaction. The moment that the treadmill does the wrong thing, obviously I feel the sensory repercussions of its motion, and that's maybe not going to be so useful. Right? Again, physical context matters here, and it's not a trivial thing to do. Okay, let's have a look at the fifth and final system. Okay, I think you get the idea. A little bit simpler and low tech, which is sometimes a good thing. What's the cost of this simpler system?
The way he was walking looked really awkward. It was stiff.
Absolutely, right? So much less natural motion, but the user never takes their foot off the floor plate. So at least in terms of safety, maybe things are a little bit safer.
How is he using his hands? They're controlling all hands.
What was he doing with his hands?
Yeah, it was only functional for his feet. It wasn't by hand.
I think he's holding a controller. You're holding the controller, but you can't see it.
It doesn't make any sense.
Maybe.
I mean, granted, you said it's simpler and probably cheaper, but I think it's by far the worst.
Yes.
So of course there's going to be, absolutely, right? So we've got low tech, so we're going to support less of the sensor motor interaction of actual moving. You're walking in an unnatural way. You can't see the repercussions of your motion and you're holding something. A little tricky.
This is not tethered.
It's not tethered, right? So part of the design decisions here were to allow no physical contact with any obstruction whatsoever, right? With the exception of the holding the console, there's nothing, no physical objects touching the user while they're moving. You'll notice from time to time they grab the handrail there. Any other advantages of this system?
Looks like it can actually fit in your house.
It's got a compact footprint.
It also looks like it might be affordable by the everyday user.
Absolutely, right? So VR systems are not necessarily accessible from a financial point of view for all of us yet. So a simpler solution. Okay, you can fill this out at your leisure. We looked at the Catwalk, which had the concave floor plate, which biggest cost is the act of walking is not supported completely. No occlusions or lag in this case, you can sit. The second one we looked at, same thing, had the concave floor plate. There were some occlusions though. They're wearing this, there was this belt around their waist. But at least it catches you if you rock back. The third one we looked at had the flat floor, so foot collision occurs exactly when you would expect it to. However, there's this sliding during walking, which throws things off a little bit. We looked at the Infinideck, which is nice, no occlusions. You're sort of free to actually move around a little bit.
How did the Cyborg one?
Yeah.
How did that make it so that you weren't? How did it make you stay in the center?
So this was the third one we looked at. How did it keep the user in the center? So it was a flat floor plate, and they had their socks on, and they were sliding.
It's the ring.
They were wearing a ring, which is maybe not physically moving you back in the center, but it's giving you a hint, because as you move, the ring is attached to the back or above, so you can feel increased pressure on the small of your back, I assume, and it gives you a hint about how to center yourself. And my guess is, assuming that the illusion is rich enough, you don't notice that you're doing that. You're moving back and you're feeling something push against your back, and maybe you move yourself a little bit forward. So you probably feel increased pressure when you're moving towards the periphery of the ring. It's my guess, but maybe you'd have to go back and watch the video. Okay, last one we looked at was pretty simple, but by being simple, it could get away without having anything actually physically touching the user in the process, but some occlusions and a very unnatural walking gait. So obviously lots of pros and cons, very difficult to support all the subtle aspects of expectation we have when we move ourselves in the world. Unfortunately, we can't all afford this technology yet, but you can simulate a cheap version of virtual reality by finding a safe environment, closing your eyes, and jumping as high as you can vertically, and not look at yourself landing. It's a tricky thing to do. One of the challenges with virtual reality, of course, is you can't actually see the physical world while you're seeing the virtual world. You're walking and running and shooting and doing all these other very physical actions blindfolded. And you better hope that the blindfold is giving you what you expect to support those activities and not harm yourself. Question?
I've seen some new development in level design where you're no longer building worlds in Euclidean space, but you design them in sort of like hyperbolic space so that you actually require less motion around your room.
Interesting.
But you still feel like you're moving through a huge world.
Exactly, right? So we live in Euclidean space, right? When I move 1 meter to my left, I can feel the repercussions of that, but the virtual world does not necessarily need to respect that coordinate system. It can project motion into a non-Euclidean space so that motion near the center is exaggerated, but as I move further and further away from where I'm supposed to be, I'm somehow restricted in my motion. Right? So it comes at a cost, of course. We're breaking the expectation that we're moving in a Euclidean space, but maybe it allows us to move freely in a smaller volume. Right? Lots of design trade-offs in virtual reality. Okay, let's move on. So we just spent a lot of time talking about physical movement. Let's talk just about the visual sense. Humans are visual creatures, and it took a long time to get virtual reality goggles to support the environment that I am looking into a world which is possibly much larger than the physical world that I'm in at the moment. Very tricky. How can I look at a virtual object that is 50 meters away if I'm in a physical room that is less than 50 meters long? Tricky, right? So we're going to talk just about that for a moment. So the way to do this is to use stereoscopic vision, which is actually a tricky thing to do. Most modern VR goggles work in the following way. Obviously, we have eyes left and right. And when we look out at the world, they are capturing, in the physical world, a partially overlapping scene. So my left eye sees about this much, and my right eye sees about this much. Why is it important? Why did higher mammals evolve stereoscopic vision? To have two eyes that partly overlap seems like kind of a waste. It'd be better to have two eyes that capture a wider range of vision. Why the redundancy? Depth perception, right? So objects that fall near the center of my field of view, I am seeing them from very slightly different angles, and the disparity in those two views of that object, the amount of disparity tells me something about the 3D shape of that object and how far away it is from me. Extremely useful. If you're looking at a VR goggles and you have one screen here and you have a second screen here, those physical screens are not overlapping, which is not what your eyes expect. And unless you do this very, very carefully, your eyes will pick up on that fact very quickly. And whatever it is that you're looking at in these two screens will collapse from 3D back to 2D, and the illusion is broken. Right? So there's some pretty sophisticated computer vision that goes on that takes a virtual environment, takes a virtual camera, places the virtual camera where a human viewer would normally be, and those two virtual cameras capture a partly overlapping scene in a 3D virtual environment. So those virtual cameras have two different 3D positions. So the virtual cameras are also capturing slightly different views of a virtual object and then projecting them back onto these two screens. So we can take care of the partially overlapping visual problem, but we still have a remaining problem, which is that the user's eyes are trained on a 2D surface that is much closer to them than the actual scene. How do we deal with that problem? The human eye is going to naturally try and focus on this two-dimensional surface that your brain knows is close to the eye. It's an automatic process. It's hard to stop that process from happening. How might we overcome this issue? Imagine you're wearing these goggles and your brain knows that it's looking at two screens, and whatever images are on those two screens are kind of blurry. How does that suddenly resolve into the perception of a 3D scene which is much further away? What needs to happen to create that illusion?
Objects that are farther away get smaller and harder to see. You can imagine like your eye test or whatever. Large objects are easy to see from far away, and as you get to small ones, they merge together in pixels.
Exactly. So we spent a lot of time talking about expectations of visual scenes, right? Smaller things are further away, larger things are close, but we're not there yet. We haven't our eyes have not resolved an image yet. There's just these sort of two blurry images a few inches away from our eyes. So we can't use any of those tricks yet. We can't use motion parallax, where objects that are further away move slower, closer objects are bigger. We need to trick the brain into thinking that it's looking at things that are further away than they actually are.
The ones that are further away have to be like less different on your right and left views, whereas the ones closer to you are like very displaced.
Exactly. So even if you haven't yet focused on the images themselves, you're just seeing these blobs, your brain might see that there is a big red blob here and a big red blob here, and they are closer to each other in the two screens than some other blue blob, which also matches in both scenes. So there are some subtle visual cues that might start to click in where your brain, like when you were looking at the Necker cube, starts to put those clues together, and your brain comes to the conclusion that if you put all these clues together, they are all pointing in the same direction, which is, I'm not looking at two images, two blobs which are sitting very close to my eyes. It's not what I'm seeing. I'm actually seeing some image that is a single image that is further away. Here is again a cheap version of this. I don't know if you can actually do this with the screen. Can anybody see something other than just the two-dimensional image here? It looks like?
Oh, the eyes overlap. Some circle of L.
Yes, perhaps a disturbing image here.
It looks like Hieronymus Bosch, like the running.
It does. You're right. Okay. Aside from the disturbing image here.
It's an eye.
It's an eye singular. Okay, so it is possible to be seen. So this is one of these optical illusions known as an auto-stereogram.
I think it's the 90s technology.
Yes, this was very popular in the 90s and early 2000s. Yeah, exactly right. You can go watch these at your leisure. So the trick or the illusion that this image is trying to project is not unlike the Necker cube and not unlike what goggles do. So I see some of you squinting, which is the right idea, right? So you are trying to alter your visual system in such a way to pick up on the clues that are hidden in here that taken together will trick your brain into seeing one large eyeball somewhere into the next classroom back there.
It's like you're changing the focal plane.
You're changing the focal plane. So what you're actually doing is altering what's known as vergence and accommodation. So I pulled this off of the Wikipedia page for autostereograms. You can go read this at your leisure. So basically what your eyes are trying to do actually all the time is obviously to take two 2D images that are falling on your retina and resolve them to see whether objects that are in those two-dimensional images, if any of those objects overlap, and if they overlap and have a certain kind of difference, that gives you a hint about how far away the object is from you. As I've mentioned several times in this class, even sitting quietly and looking at the screen is not a passive experience. It might feel like it is. But while you are doing that, you are altering vergence and accommodation. So vergence has to do with two eyes, and accommodation has to do with a single eye. So let's do vergence first. So vergence is the horizontal angle of your two eyes relative to one another. So as the clues are coming in from the two 2D images, your brain is making predictions about what is out there. Maybe there is an object much closer to me than I actually think, so I will go a little bit more cross-eyed and bring both of my visual fields to overlap more closer to me. And I'll see whether the evidence stacks up. If it doesn't, perhaps the object is further away from me, and I will move my eyes apart so my visual fields are now converging much further away from me.
It's super interesting because like I used to have to set like when 3D cameras came out, I was a camera technician, and they had a beam splitter device to the camera.
Okay.
And they would have to physically set the convergence point based on the lens of the camera. So it's like they're setting how far away.
Yes, you do have to do the same thing with cameras, right? So cameras do a version of this. As always, human eyes do this much better than our camera, even our most modern cameras yet. So vergence is trying to figure out, is focusing on some object, or I'm not focused on an object yet. There is some blob out there which appears in both scenes from both eyes. How far away is that blob from me? So I am trying to basically focus two beams of light on that object. If I'm wrong, for example, in this case, my brain is guessing that the object is much closer to me, and I focus my eyes on it, and I get two views of that object, and I'm wrong. What visual clues are telling me that I'm wrong, and maybe I should verge further away? So imagine I'm actually looking at an object that is very far away, but for a moment I think it's much closer, and I become a little bit more cross-eyed. That far object is still in both scenes of my eyes. What evidence tells me that I was wrong? It's not where I thought it was.
Kind of like, if I were to look at you and go cross-eyed, you'll be here.
Exactly. So the objects will switch over and start to move in opposite directions in the two scenes coming back from my eyes. If you sort of imagine the object is out here, right? So again, I've made an action and I've received a sensory repercussion of that action. Alternatively, if I do this, the blobs may still be out of focus, but I might notice that the relative angle of the two blobs, so the relative rotation of these blobs in my two visual scenes is very small. The difference is small, and that is a clue that the object is further away, right? Objects that are further away, if you're looking at them, you're going to see more or less the same sides of the object. An object that is very close, my eyes are seeing very different parts of the object. That's vergence. However, it's still a blob. It's not focused yet. So accommodation is actually muscles in the eye that change the 3D shape of your retina, again, like a camera, causing you to try and focus your vision at a certain depth of field. So these two, when you're squinting at the audio stereogram, that's exactly what your eyes are doing. And if you relax your eyes a little bit and try and let your natural, let your brain dictate what your eyes should do, for most people, eventually there are certain clues in here that suggest that your eyes should adopt the wall-eyed vergence, which is your eyes are more or less parallel and you're looking not at the image but through the image. So imagine that you could see into the next classroom back here and you're trying to look at some hypothetical object in the center of the classroom behind the blackboard. If you do that, for some people, you might then start to see that in fact there is an object further in to the image. And in that case, accommodation kicks in and the muscles controlling the shape of your retinas flex and relax and try and resolve the image. And for some of you, you might actually see the single eye in the image. Now, it depends on how far away you are from the illustration, so some of you in the back may not be able to do that.
I think if we project that on the wall, we actually cannot do the parallel method. What I use is the cross-eye method, so I can see the picture. Because,
okay.
Because it's this distance is already use your most parallel eye.
Okay.
Yeah, so you cannot see the actual things using parallel more. You cannot separate your eyeballs to both sides. So this one you can use cross-eye.
Maybe that's what's actually happening. Again, it's an illusion. So what you would actually be doing if you were trying to focus an object that's in the next room, maybe that's not what's actually happening. The point here for us is that given the visual clues in here, which like the Necker cube, these clues are designed in a very sneaky way to trigger certain inbuilt reactions that you have when you're trying to focus on various objects at different distances away from you. Yes?
What's the difference between this and I was looking at some picture a few days back, and instead of it being like far away, you look at it pops out as a 3D kind of image. I had to really, really blur my vision.
I would imagine it's very similar to this, right? So there are certain clues that you can give to the human visual system that suggest the object is closer to you. Like, for example, two blobs which look similar. They're both in they're in both field of view for each eye, but you're seeing very different views of that object. If that's actually hidden in something like an audio stereogram, that suggests to your brain that you should verge closer to you. Right?
Can you point out, just try to give me a little tip here?
I can't do it from my angle. Can you draw it on the board?
I can show you. Yeah. Like there's an eye here and there's an eye here. Those two eyes are similar. Then cross your eye to make those two converge, and then you can see the whole picture.
Can you sketch with your finger where the actual large single eye is? No, the thing that's hidden.
You can convert my finger. One's here, and you can convert that so you can see the.
Tricky, huh?
Cross your eye. Don't use parallel. Cross your eye, like you are watching your nose, like you're watching your nose. It's like a little bit stupid.
Okay,
yeah.
Thank you. All right, we could spend all day. They're fascinating. My suggestion is, I know you all have a lot of homework. When you get half an hour of free time, sit down with one of these and see if you can figure it out. Another interesting point about auto stereograms is it's very hard to give explicit instructions to someone about how to do it, right? Very difficult. It's better to give visual cues. Let the brain do what it naturally does, which is rely on the 20 or 30 or 40 years experience it has with looking at two partially overlapping 2D scenes and take hints out of there about what is actually out there. Okay, I'm going to move on. Okay, so here's Oculus Rift, sort of the state of the art in VR goggles. Here is a bird's eye view of what someone sees inside the goggles, and they're obviously seeing not an auto stereogram, but auto stereograms are a single image optical illusion. You can also do it with 2 images, which is what VR goggles do. This one, I don't think you can cross your eyes and actually see the 3D illusion in here, unless maybe you're sitting far in the back. But just looking at the differences in these 2 images, what is the difference? What are the differences in these 2 images that are suggesting what's further away and what's closer to the goggle wearer? We just talked about some of them, but there's some additional clues in here.
The items on the ground are shifted to the edge of each box on the right hand.
So the objects that are on the ground, you can see, are shifted a fair bit from one image to the left, one image to the next.
I think the images that are, or the items that are closer are between the 2 images are farther apart than the ones that are farther away, which are maybe not quite more centered or not as far away.
Exactly. So the objects that are further away, like the buildings in the background, they are actually horizontally displaced less than the objects that are closer, right? Which is a version of parallax that we talked about, which had to do with motion, but this is also true for 2 stationary objects like your eyes, looking at multiple objects, and some of which are further away than others. So it's not just the relative angle at which your 2 eyes are seeing the objects, but also their relative positions in your 2 fields of view. And if you really pay attention to this picture, you might notice that some of the close objects, like the gun or whatever this thing the user is carrying, we're actually seeing 2 different views onto that object, whereas the further objects, we're seeing them, the angle at which we're seeing them is closer between the 2 images. Again, a little hard to see, but it's there. Yes? Yes?
Each user have to tune the system to their
Good question. Is there any tuning that needs to go on? Are these general heuristics that we just talked about, are they true for any human wearer of the device? So you've been paying attention in HCI, right? The answer is usually no. There are human differences that mean that this isn't going to work perfectly for everyone. What are the human differences that matter here?
The pupil distance is very important.
Pupil distance, absolutely, right? So the width between my 2 eyes is different than the widths of your 2 eyes. It's slight, it's small, but it matters if you're looking at objects that are very close to you at the same time that you are looking at objects that are very far away from you. So VR goggles works pretty well for pretty much everyone, but there is, in some of these devices, a little bit of tuning that goes on based on the actual horizontal separation of your eyes.
So I noticed that they're always kind of curved in VR goggles.
Yep.
When you put it on, that building on the right when it simulates curve, how does that work?
Why are they curved? What's keystoning, for those who don't know?
Like when you're photographing a building, it's not flat on to show depth.
Yep.
It's typically they call it keystone, or it narrows, converges
right
as you go up more.
Exactly. So it's related to that. So if you think about, actually, you can probably see it in the boxes here. So the edges of these cubes, of these boxes, are not perfectly straight. They're curved because the box as a whole is not at an exact distance from you. Different parts of the box are at different distances from you. They're slight, but they're there.
This is just a question about VR. Does the VR system actually make those curves, or does the artist who's making the game have to basically make a whole new rendition?
That is a good question. I don't know the answer to that. That would be a good one to look into. Yep.
I think the curve is because when you look at some picture, if the picture is you put the picture very near your eye,
yep.
you need those curve to make the line in your perspective a straight line.
That's true. So there's many reasons for the curvature. Another reason, as you mentioned, is dealing with the fact that there is a physical object which is projecting the image very close to your eye, which is usually not true in reality, right? Most objects are pretty far away. Obviously, if you look at an object very close up, it's usually out of focus unless you really work at vergence and accommodation, right? Your eyes have to work very hard to resolve or focus on objects which are very close to you. So adding curvature helps that process and actually helps you to stop doing this and relax your eyes and start to do this, which creates the illusion, right? So when you see 3D in virtual reality goggles, you are actually not doing this, you are doing this, which is what you need to do to see the hidden illusion in here. You need to look past the plane of the screen and look into the screen. Of course, you're not looking at something behind the screen. You're still looking at the screen, but your eyes are collecting different parts of those two screens in VR goggles.
One thing that always trips me out too is like, it's not realistic of height either. So if you
not realistic of height.
Yeah, so if you have a really short person and a really tall person, and when they put on the goggles,
interesting.
Wise, and then also a lot of the 3D rendering programs like Maya and stuff are, when you render a world, it's mapped onto a sphere.
Yep.
So because of like light occlusion and all that stuff, so it makes sense that it's not flat. It's not, they don't project the world onto the...
Exactly. So if you're an artist for a VR game, you have to think very carefully about projection. Somebody mentioned non-Euclidean geometry. It is not enough to just register, to render a Cartesian scene where everything is at right angles. It is non-trivial to present visual cues to allow someone to look through the goggles and see the 3D scene behind the goggles. Okay, I think we will stop there for today. You have a quiz due tonight. You're working on interim video 2, and I will see you all next Tuesday. Thank you.